Hi, in this video we're going to discuss a different type of an IP model, which is called a mixed integer model. In all the LP and general integer model examples that we've studied so far, we are typically dealing with situations where the cost is directly proportional to the quantity of the decision variables. So for example, if the cost to ship a certain item is $10 and I decide to ship 5 of those items, then my total cost becomes $50. However, there are situations when there are fixed costs in addition to these variable costs that we just discussed. These fixed costs may include costs such as setting up machinery for the production run, or setting up the construction of a new facility, design costs to develop a new product. Unlike variable costs, these fixed costs are independent of how much of the product we produce. You are going to incur these fixed costs even when the quantity of production is small or high. So when we have problems like that, where both fixed and variable costs are included, it's a classic example of a mixed integer model, and we call these models fixed charge problems. So fixed charge problems are problems that include fixed cost in addition to variable cost. We're going to use binary variables to model the fixed cost portion, and we're going to use linear or integer variables, general integer variables, for the variable costs. Because now we have both types of these variables in our model, it is a mixed integer model because we're allowing our decision variables to take either binary values for the fixed cost, or have linear or integer values for the variable cost. So in order to demonstrate this model, we're going to use an example to help us understand how to model these type of problems. The example that we are going to use for a mixed integer problem is the example of Hargrave machine. This is directly taken from the book, so you can find the full description and background of the problem in the book, chapter 6, but I'll just give you a brief summary of what the problem is. Hargrave Machine Company produces computer components at its factories, which are located in Cincinnati, Kansas City, and Pittsburgh. Now, these factories have not been able to keep up with the demand that Hargrave Machinery has been having in the 4 warehouses, which are in Detroit, Houston, New York, and Los Angeles. So they are deciding to build a new factory so that their production capacity is expanded. And the 2 sites that they're considering for their new factory is in Seattle and Birmingham. So both these cities are attractive in terms of labor supply, the municipal services, infrastructure, ease of the factory financing, and all of that. So in this table over here, what you see is that the production costs and the monthly supplies at each of these 3 factories, as well as the monthly demand for each of the warehouses, has been given. In addition to this information, Hargrave also estimates that the monthly fixed cost for operating the proposed facility in Seattle would be around $400,000, and the Birmingham plant would be somewhat cheaper due to the lower cost of living in that location. So Hargrave therefore estimates that the monthly fixed cost of operating the facility in Birmingham would be $325,000. Note that the fixed cost at each of these existing plants does not need to be considered here because we've already incurred them, we've already paid for them, so they are not a part of our decision anymore. What those are labeled as are sunk costs because they're not considered in this optimization model. They are costs which have already incurred and we don't need to take them into consideration for this decision-making purpose. This next table here gives you the unit cost of shipping from each of these plants to each of the warehouses, and they've also added the shipping costs for the potential new factories at Seattle and Birmingham. In addition to this, the solution needs to consider the monthly fixed cost as well that we just discussed. So now we have all the information that is available for us to move to model formulation. We're going to use this table and the table on the previous slide to help us formulate our decision variables and our final model to get the solution. So let's discuss how we're going to start the formulation of this particular model. The first step obviously is to formulate and define our decision variables. What are the decisions that you need to make as a result of the solution for this problem? The decision is obviously two types. So the first decision that we need to make is, I'll call this decision number 1. It's to decide which of the 2 factory locations would you select for the new plant. The first option is Seattle and the second option is Birmingham, Alabama. The second decision that the managers need to make, I'll call this decision number 2, is to decide on what quantity of goods should be shipped from each plant to each warehouse. So this is your typical transportation model that we are going to be formulating. So with the help of a mixed integer problem, we're making 2 decisions at the same time. The first part of the decision is to decide between these 2 factories which one should be selected, and the second part is, once we've selected the factory, how much product should be shipped from that factory and the previous factories which are already existing to the warehouses where the demand is there. So to do that, we're going to define our decision variables as 2 different types of decision variables. The first decision variable is a binary decision variable, and this is relating to decision number 1. So I'm just going to write D1 in front of it here, and the first decision that we need to make, if you recall, is whether or not we should select Seattle or Birmingham for our new plant. So let's call this decision variable YS, and this is specifically for the Seattle plant, and YS is defined as a binary variable. So just like the previous examples for binary models that we did, YS can take a 1 value if Seattle is selected and 0 value if Seattle is not selected. The same way YB can take 1 value if Birmingham is selected and 0 value if Birmingham is not selected. Now, you have to note that these 2 decision variables here are mutually exclusive because only one of them can take 1 value and the other has to be 0. If this one is 1, the other one has to be 0. Then we have our regular decision variables for our transportation model, which is deciding the quantity that needs to be shipped from each plant to each warehouse. Now, the plants are in Cincinnati, Kansas, Pittsburgh, Seattle, or Birmingham. We're going to include both of them into our model because the first part will take care of dropping one of these out. And the second subscript here, J, is for the warehouses, which are in Detroit, Houston, New York, and Los Angeles. So now we have defined 2 different types of decision variables, which is the whole criteria of a mixed integer problem. The first one is a binary integer variable, and the second one is a general linear programming variable which does not have any restrictions on it for it to be integer or for it to be binary or not. Now we move on to defining our objective function. The objective function is to minimize total cost, and these total costs are a combination of both our fixed cost for setting up a new factory as well as the shipping cost for transporting goods from the factories to the warehouses. So because this part over here is similar to a transportation model, I'm going to use the second table which was given to us as a part of the question, which had the shipping cost associated with each factory and each warehouse here to form the first part of my objective function. So this part over here, which you see on the screen, is for the overall shipping cost, total shipping cost for our model. The second part which you need to add is this lower line here, which refers to the setting up cost of a factory, either in Seattle or in Birmingham. We said that the fixed cost to set up a factory in Seattle is $400,000, whereas the fixed cost in Birmingham is $325,000. So now our objective function is complete and we can move on to the constraints. If you recall from transportation models, for every transportation model, you need to have net flow balance equations. And that's what you see on the screen here for the top and this bottom set of constraints that you see. Ignore this last constraint for now. I will explain it as soon as we're done with these top constraints. So I want you to focus on this first chunk of constraints that we have up here. As you all can recall, that for a net flow equation, the way we calculate it is that inflow has to be there minus the outflow, which is equal to the net flow for that particular node. Now, because if we look at the factory nodes first, the inflow in each of these factories is set to 0 because they are pure supply nodes, and the outflow will depend on which warehouse they send out to. So for the first node, Cincinnati can send out to Detroit, to Houston, and so on. The same way for Kansas, for Pittsburgh, Seattle, and Birmingham. And because these are pure supply nodes, we force the right-hand side values to be negative. These are the values that come from the first table in the problem, and these are the capacities at each factory. One thing that you'll notice here is that for the Seattle and Birmingham factories, which are the new factories, they are not set up yet, we have added the binary decision variables as a part of the right hand side. The reason for that is only one of these factories is going to be set up eventually, not both of them. So we need to make sure that Excel knows that one of these need to be 0 and the other needs to be 1. So that's why by multiplying the capacity with these binary variables, we're making sure that when Excel selects Seattle, for example, Birmingham automatically just becomes 0 and this equation is not applied anymore to our model. Then the second set of equations over here are for the pure demand nodes. We all know that for the demand nodes, there is no outflow, so the outflow is 0. And these are just the inflows into each of these warehouses. And finally, we have the last constraint, which makes sure that the mutually exclusive constraint, we select either one of the two options, Seattle or Birmingham, either Seattle or Birmingham, and forcing it to be equal to 1, so that when one is 1, the other can be 0. So now we have the set of all our constraints ready here for us to move to Excel. I've switched my screen to Excel and I've sort of created a blank template here for me to work out of. The template that I'm following is for a transportation model, which is why you see this table type format here again with the flow out, flow in rows and columns, and the network flow balance equations. So the setup here is similar to what we have in a transportation model, except that now we have this additional portion here, which I added for my binary decision variables, which will decide whether Birmingham should be selected or Seattle should be selected. And I've also set up rows here where I can calculate what my total shipping cost, what my total fixed cost, and eventually the sum of these two will be. I've also added the additional constraint regarding the binary variables so that we can make sure that only one of the new plants is selected for construction and not both of them. So now I'll start filling out the formulas over here that are required for me to solve this particular problem in Solver. The first part is to define my decision variables, and I will highlight these cells that I've selected here in yellow so that I can remember that this is where the decision variable values will be stored. And just like any other transportation model, you're going to first find out the sum for each of these origin nodes, and because this is across the row, I can simply drag this down without formatting, and these would be the flow out numbers for each of these factory nodes. Then I'm going to get the sum for flow in for each of the warehouses. So I'll sum down the column and drag the formula all the way across without formatting. Now, because these are cells with formulas in them, I want to highlight them in blue because in transportation models, it's very easy to forget which cells have manually coded numbers in them and which cells have formulas in them when you see zeros everywhere. So the shipping costs, I've already added them. These are directly taken from the table which was given to us as a part of the question. Next, I'm going to highlight my other decision variables, which are the binary decision variables, and this is the YS and YB decision variables that we considered during the model formulation phase. So now I'm going to calculate the total shipping cost, which would be a sum product of the top yellow cells with the bottom box of unit shipping costs. Next, I'm going to calculate the total fixed cost, which would be the sum product of the second set of decision variables with the second set of fixed costs per decision variable here. And finally, the total cost would just be a sum of these two values here. And this total cost is going to serve as my objective function, so I'll highlight this in green and put a min in front of it. Next, I'm going to populate my constraint equations, which are my network flow balance equations. So first, I'll add the flow in, which is for Cincinnati, Kansas, Pittsburgh, Birmingham, and Seattle. These numbers would just be equal to 0 because these are pure supply nodes. And the flow out for these would be these vertical columns right parallel to them, where we're calculating the sum that is shipped from each factory to each of the warehouses. And I can simply drag this down without formatting. And next, I will set up the left-hand side of my constraint equations where the net flow is calculated, which is inflow minus the outflow. And again, drag this down as well. Now I'll highlight these two sets of cells here so that They are in blue so that I can differentiate between this 0 and this 0. This is 0 because I haven't run solver yet, and this is 0 because these are supply nodes. So just to make that difference clear, I'm adding this blue color coding. I've already added the capacity constraints for these nodes here. For the Birmingham and Seattle factories that are going to be formed, and this model will help us decide which one should be formed. If you remember from the model formulation, this side was also a formula with a variable in it, and these were the binary variables. So the overall capacity for each of these factories is 11,000. And we did not just add 11,000, but we added 11,000 and multiplied it with their respective binary decision variable here. So sorry, let me put an equal sign and then start. 11,000 multiplied by the binary variable for Birmingham, and 11,000 multiplied by the binary variable for Seattle. And because, again, these are pure supply nodes, I'll force a negative sign in front of each of these. Don't forget the negative sign, because then your solution would be all messed up if you forget the negative sign over here. And again, because these two cells have formulas in them, I'll highlight them in blue. Next, I'm going to move on to the network flow balance equations for the warehouses. The flow into each of these warehouses are given by these cells here. So I'll manually add them. I cannot copy paste these ones because here I'm putting them in a column format and here they are in a row format, so dragging is not going to help. And finally, E10 for LA. And the flow out of these warehouses is 0, so I'll manually type a 0 in there. Again, put a blue cell here, and the net flow equation would just be inflow minus the outflow, and drag it down and highlight in blue because they are formulas. I've already added the demand requirements here, and we don't need to do anything here. Finally, then the last constraint would be the ys plus yb has to be equal to 1, because we need to select only one factory out of the 2 new locations to be built. So the left hand side would simply be the sum of these 2 numbers here. Sorry. Let me write that again. This will be the sum of these 2 numbers here in yellow, and this needs to be equal to, equal, enter, I always forget, and 1. So now our model is set up and we can move on to solver to get the solution. I've opened up my solver window and I'm going to fill it out now. The objective is set to this green cell here where I'm calculating total cost. I want to minimize this subject to the changing variables, which are these yellow cells here, and with a comma, these 2 yellow cells here. Next, I'll add my constraint equations. The first set of constraint equations is for the net flow equations, and then I need to make sure that these cells here are equal to the right hand side values. Next would be this additional constraint here that we added to the model to make sure that only one plant is selected to be constructed out of the 2 options, which is this cell here needs to be equal to this cell here. And then finally, our last constraint is the fact that these 2 decision variables need to be binary. So I'm going to add that by putting the cell reference to only these 2, and under the drop down I'll select binary and press OK. Now I've added everything that I need to solve the problem, and I can hit solve. So after I hit solve, I have my solution ready here, and the solution is telling me to select the factory in Birmingham as the new location, and these are the quantities that need to be shipped from each of these factories to each of these warehouses so that all of our demand and capacity constraints are met.